Nope.
Oh, I know.
Alright. I have ice here.
Ah.
And the ice should all be the same temperature. However, this doesn't work well with, it's working.
Negative 1.8. Negative 2.6.
Let's just say negative 2.
Negative
Is
2.4.
that
Celsius, yeah.
Yes, centigrade.
Yeah, 2.0. Negative 2.0 is good.
Centigrade. This
Alright.
is hot
Can you
water.
write that down for me? Yes, that is
How
hot.
can you tell? I can tell.
The thing is kind of.
There's water evaporating from it.
Look very closely.
Again, it's not 100 degrees.
Oh, yeah.
Why?
The steam.
This is 70 degrees.
It's 70 degrees and it's
Write
evaporating.
those down.
We still have to talk about that.
Yeah, let's do that.
Yeah, we will.
Did anyone come up with any hypotheses?
No.
And there's cold water.
Mix,
that's 9
too.
degrees.
That's the
What
way God made it.
what's
That's the hot water. Cold water is 9 degrees.
The hot water, Sue, it's 70 degrees C and it's evaporating. You can see it.
See steam?
Water doesn't
I can
evaporate
feel it.
until it gets to
Oh,
100
no,
degrees.
listen. Moist.
100. What is it called?
7. Wait.
7?
Maybe it was 9.
It was 9.
Yeah, it was 9. Which is 48.5 Fahrenheit.
That's crazy. Percentage difference between the cold water and the hot water, and it's still being water.
Hot.
Well, the cold water is close to ice than it is the hot water, right? Right?
What?
The cold water is closer to ice than it is to hot water, right?
Yeah.
Wrong.
Temperature-wise, yes.
Temperature-wise, it is. That doesn't mean squat.
Energy-wise.
Why? Energy-wise, it's not even near.
What? Oh, okay. I got you.
Because the amount of energy in the phase change, actually it's probably near, but I still think it's more energy difference between these two than there is between these two. Anywho.
Alright, so I'm going to do a hot and cold for each one here. We have half full of ice, fully full of ice, and no ice at all. And so this will just show how it cools off just in
Be
contact
careful,
with the air.
guys. I'm just joking.
Yeah, that's right. The cold water might burn you.
No, I mean, the explosion that's ensuing.
Not
Be
pouring
careful.
acid
Don't
into
take
water.
this too lightly.
Alright, and what's going to happen when I pour the hot water
Scratch it.
into these?
Might have magnesium.
Do you think it'll melt at all?
Wait, is it
I think
magnesium?
it'll be
Eventually,
steaming more.
eventually it will melt it all.
Yeah.
Okay.
It'll be steaming.
Okay. Do you think this one might melt it all the way at once? Or just a little?
Not at once.
Okay. Alright, well, let's do that.
Whenever I put something hot in cold water, it steams more. Whoa, whoa. I think I was so
Now I'm trying to put about the same amount of water in each one. Well, so why is this one higher
because there's more stuff in
and
it.
more volume to start with, right?
You're gonna go with this now?
Yeah. Here, put the cover on the pour easier, actually.
Be careful. We're mixing water and ice, so.
Slowly, I drink.
Is that about level?
No.
Yeah.
So if there's glasses watching water melt, I mean,
Watching water
melt.
Ha! Good thing you don't teach science.
it is a good thing. I need to interrupt you though.
Me?
Yes.
Okay.
Rachel has a new computer thing and there's about 5 computers that are locked and no one can open them.
Okay, I'll be there in a second.
Sure.
Okay, we're at,
So now, this, guys, this is a surface temperature taker. And so,
let's do this. Let's put a sheet in front of each one so we can log temperatures.
what do you want to take, every minute?
I don't know, not necessarily. I was thinking maybe 10 minutes.
10 minutes, okay.
So you said he wants to do everything.
So, someone come up here and help Mr. Ernstock because I need to go and,
Rescue Mrs. Peeler.
yes.
Do you need any help? That was in my eye. That would have been dangerous.
No, it's not the same as a laser pointer.
They're not.
No.
I'm not going without my coffee.
I mean, it's a
The laser is not what measures temperature. The laser is just a
She
an
wants.
aim.
Sue's
okay?
head is 27 degrees.
The actual thing measuring temperature is this here. It's an infrared sensor. What's infrared light?
invisible.
Light we can't see that gives us heat.
But
Yeah.
if you stand
Anna
for
is warmer than Sue. That's not a surprise. Sue is cold.
I was waiting for that.
27 is not true. It's not human body temperature.
That's what you don't understand what this is, Sue.
This is a surface, not the.
This is a surface temperature.
no,
tape.
but it on the side it say if you like measure from the
You're
far,
right.
Yeah.
it's gonna
Because
measure
actually my
from the
surface
line.
is 90.
It's gonna
Yeah,
make
it is
what?
measuring your
You're right, Sue. It
body
doesn't.
temperature.
Surface.
That isn't a human's body.
Your surface temperature is not 36 degrees, Sue. Open your mouth.
No, if you measure, if you
Sue,
measure,
open your mouth.
no, if you measure the
Open
mouth
wide. This is
Or no.
32 now.
No,
Why?
Listen to me. I'm not gonna say anything.
you can measure her mouth from there because infrared is going wider when
Yeah,
you go closer.
Mr.
So
G
it's
told
like-
us that yesterday.
It measured it. She was 32 when she opened her mouth, and she was 28 when she didn't. So, hold on.
So you measured her whole
It's-
height when you.
No, you don't know that. Hold on. Meters.
Someone did that to me in the airport.
Your
2
body
years ago.
temperature.
That thing.
Wait, what?
No, it's actually 4 years ago. I
Like,
was
it
in
measured
Hong
that
Kong
you
and
have.
I walked in.
How many meters? 2 meters.
No one just take one.
This is taking Mick.
Trying to make sure you don't sit.
This is not. This is far from it's a 1 inch to no. It's 1 inch to 8 meters. So we're 2 meters away. So it's measuring a quarter of an inch.
Oh. Oh, so it's that far.
Yes.
Oh.
So now, if I measure across that way, because that's 8 meters away, it's measuring an inch. Look at the spot; it's about an inch. See?
Oh,
Can I?
interesting.
So Sue, were you wrong?
Can you get the?
Were you wrong, Sue?
Can I get the temperature of the second? cup?
Yeah, coming in on the right.
What?
Were you coming right?
Oh.
5 degrees C.
Can you put that measure from here?
I messed it up.
That won't be the same.
Of course it won't, because I'm measuring the surface temperature of the water, and you'd be measuring the surface temperature of the cup. Cup is an insulator, water's not. 2.2.
You can measure from there. Measure the cup.
17. 2.0. 51. 12. Now what's wrong, Sue?
Measure the cup's temperature from your where you are.
What's under that?
Near.
12.
Closer.
8, 10,
That's 1.
1.
But see,
Can I have it from here?
-2.
Yeah.
1.
See?
8.6, 11.
Wow.
What's your point?
Big difference.
The further away, the less temperature?
Yeah.
Yeah. The less heat it's going to measure. But it doesn't change the fact that this still measures surface. The surface of your skin, that was the point that I was making. The surface of your skin is not 36 degrees.
It is.
No, it's not.
Really hot though. Because
It's not. I mean,
Do you have a favorite? Yeah, it's about 96 degrees.
33. How close do you want me to get? 30. That's awesome. 34.
Yay.
But the surface of your
What kind of
temperature, the
volume?
surface of your body is not 98. For us, it's not 98.6 degrees. Under your armpit is, under your tongue is, but because your face and your skin is constantly releasing heat, you know what I'm saying, or no? You can't take a thermometer.
Yeah, but for your mouth temperature is higher.
Yeah.
That might.
It's not 36. It's like 38.
No, it's not. How do you take your temperature?
Use it. That
Under your tongue or here.
But normally,
I
the
never
first
heard
thing
that.
to do is
Yeah.
to
Still your head, because but Sue, it's still relative. Do you understand that or no? Your skin temperature is not 36 degrees. Your mouth under your tongue is. Under your armpit is. But it takes a lot longer under your armpit to take your temperature. Because that is being released. Versus your mouth, closed. So heat doesn't get released because it's insulated by your lips.
here.
Under here, but you couldn't take your temperature under here like this. Closed. Insulated. Right? Does that make sense? Because the skin is in the presence of air, air is 70, skin is, ideally, yeah, your skin would be 98.6 or 36 degrees, but it's constantly releasing heat, you know?
Whatever you're right.
You are angsty. You were just sassy the last few days. Very sassy. You don't have to go, ah.
No, I'm saying you're right.
I know, but it's not what you said, it's how you say it. You know, do you understand that?
Yeah.
Okay, just checking. But anyways, it should make sense that your skin is trying to be 98.6 degrees or 36 degrees, but it can't be. For the same reason that this ice is trying to be 0, but right now it can't be. In fact, it's to the point where it's no longer even ice anymore because
Because there's too much heat.
because it's ice is what's happening to the ice? And is it endothermic or what's the other one?
Endothermic,
What?
exothermic?
It's taking.
Endothermic or exothermic?
Endothermic.
Why?
Because it's
taking in heat.
It's taking in energy. The ice is gaining energy. Your skin, endothermic or exothermic? Exo, it's losing relative to the mouth or under your armpit. You know, ideally, sure, you can take your temperature here, but it's not going to be the same. So the reason why is your hand colder than your head?
It's farther away from your core.
Beautiful, because it's farther away from your core, less blood vessels. So
And your head knows, or your body knows that your head needs the blood more than your fingers do.
right. You're anything that's closer to your heart is going to be warmer. That's why, you know, the first thing that gets frostbitten is your toes. Your ears are colder than your head, you know, because they're further away, less blood vessels. So if you truly wanted to find your core body temperature, you'd have to stick a thermometer right in here, but that wouldn't be helpful.
Yeah.
We should probably.
We took the first one at 25. Let's do it every 5 minutes.
Yeah, let's do it every 5 because this one's almost done being melted. What do you think the temperature this one is? It's 5C the first time. I think it's warmer or cooler. You think it's warmer now?
It's so dependent, man, on
It
how
is,
far
yeah.
you are away. That's why
The trouble is our reflective
I don't
too.
like this. I like that for the water because this just measures surface. You know,
Yeah.
we were playing around with that too. When we moved it from here to here to here, it went from 2 to 5 to 12.
Well, yeah, it's the margin of error.
But that's not because did you read the?
Yes.
We looked at that too. For every 8 meters, it's 1 inch.
No. That's-
Yes.
Those are different scales.
Right.
No. This is for every 0.8 meters, it's 0.6 meters. For every 24 inches is 3 inches. It's a
Oh,
one-inch
okay.
scale.
So it's 8. So it still is 8 to 1. Okay. So that, but still, when
8 to
we're
1
8
meter,
meters
yeah.
away, it's measuring a quarter meter across, which is less than a foot. So when we're a foot, or
If we are 24 inches away, it's measuring a 3-foot circular area.
but if we're
A
8
3
inches away,
inch
which we're
diameter.
less, it's measuring an inch.
Right.
Okay. So if we're 2 meters away,
Nick was right.
we're measuring. Hold
Yeah,
on.
Nick and I talked about it yesterday.
Yeah.
When we're 2 meters, but I was reading this. When we're 2 meters
We were
away,
too. We were reading it right. Sorry, keep going.
when we're 2, hold on, when we're 2 meters away. So why, when I pointed at her mouth, is it higher than when I pointed at her face?
Because it's like a margin of error thing. It's taking like an average of that whole area, and most of that's her mouth, and so the average temperature is warmer.
Most of that's her mouth. 2 meters, 1/4,
We need to take
1/8.
these temperatures before the rest.
Why are we using this?
What do you want to use?
A thermometer.
Okay, use it.
Because
I don't have
that's
6 of them though. I only have 3.
That's inaccurate. You were correct, Sue. Did you notice the tone? Was not like that. You were correct. I was wrong.
But I didn't think it that way. The whole region?
The what?
Um,
Oh crap, it has to be connected.
These aren't going to work. They're too thick. I wonder if Lori has anything better.
You understand what I'm saying? If there's
I know
a
what you're
10
saying, yeah.
if there's a 10-degree variance from here to here, that's nuts.
yeah.
Let me try something.
The problem with these is they have to be
Put it
connected.
in the water.
Hey, that's good. It's right at freezing. No, that's good because you know what I did? I took the air out of the equation.
You
Okay? The center's recessed. Okay?
you're gonna mess that up.
No, I'm not going to dip it all the way in. Just a little bit's not going to hurt anything. The center's 2 inches back in there. All right, so that's right at 0. What do you think this one's at?
I don't know.
You know what you're gonna do with.
Ooh, lit up.
Negative 1.8. But there's liquid in there. How does that work? Negative 1.8, there's liquid in there. Remember what the ice was originally?
15.
And I have some ice.
Negative point or negative 1. 15 for that right one. I can't get these.
What do you get for it?
10.
That one doesn't make any sense.
Right.
Because it should be getting warmer.
Yeah, this should be the.
Ooh.
But that's again, if I measure from up here, it says 16.
What if we measure from underneath?
I don't know.
10.6. Well, if you release it, it'll still tell you the last temperature percent, so you can release it and look at it yourself if you don't believe it.
It's not a matter of not believing, but
I know.
the fact of the matter is because the plastic is an insulator, it's going to vary. It wouldn't vary as much. But
Yeah.
the air is probably the bigger thing.
I got these instead of styrofoam cups for that very reason. I didn't want too much insulation.
Right. Interesting.
So this one should be cooling off too. This one actually feels a whole lot cooler than when we put it in there.
When you take it out, you are
Your
putting
hands
it
What do you
in
think?
there.
It's negligible. Actually, no, my hand's cooling it down. My hand's 37 or less. This is 46 still.
Wow.
Because it's still above body temperature. This is like a warm bath right now. Feel it. Look at your finger.
I would, but it
Temperature,
makes
take a
me
shower in the
down.
bath.
I would like to take a bath in that.
I shower
Yeah.
probably like 5th.
What?
It's like scorching.
Oh, I shower
50
so
C.
hot.
Mick, do you want to feel? Oh,
That's
did
about
it?
11.6.
Oh, it feels good. Ah.
I took a, Henry likes it when I take a bath with him, so I was taking a bath with Henry last night.
It's awesome.
And so, he doesn't know it. I
What is
give
it,
in,
27 is room temp?
and I said, Henry, watch the water as it gets in, it's going to displace, it's going to get higher.
25.
And I said, what principle is that? He's like, I don't know. Because he doesn't remember the names, but I asked him, okay, is it Bernoulli, Archimedes, or Pascal? He's like, Archimedes. I'm like, yep, you got it, kid.
Weird.
Alright.
You know what? He'll probably beat all of us in physics.
He'll be ready for physics, that's for sure.
Yeah. It'll be like the easiest class for him.
So why did they change so drastically from the beginning? Would you agree with this assessment pre-water?
What?
It depends on the temperature of the ice, honestly, because we didn't know the ice was right at melting point. In fact, we know it was -2.
The circle thing is.
Which makes sense, I think. I don't know what the freezer in there is, but my freezer is at -1.
You understand what he's saying?
My freezer at home is at 0 degrees Fahrenheit, which is like negative.
Yeah.
What?
No, I put up there those 6 glasses, and you've got ice in the first 4 and room temperature for the other 2.
Ideal?
What?
So that's the ideal situation.
Is that ideal? What?
Situation.
Ideal situation? No, I'm asking if this is what it was before we dumped the water in.
Oh,
Awesome. Thanks.
You know, when we took temperature prior to water being in,
yeah.
it probably is not. It's probably wrong. Because, as Mr. Gottschalk said, chances are the ice is less than 0 degrees C. It's probably colder
Okay,
than 0
so-
degrees C.
Please.
Does that make sense?
Yeah. How much is 25 in Fahrenheit?
About
80.
70.
Um,
Well,
So-
Mick, I'm trusting
6.
Mick. What is
so
20?
then it's been heating up.
25 is room temperature.
Because
Here
you
or
said
in Thailand?
70.
I say 86. I say it's.
No, I bet no. It's around 72.
Maybe I think of 30.
Yeah, it's around 72.
I know 20 is 68. I know that for sure. 20 degrees Celsius is 68 Fahrenheit.
It
One-
can't be 30.
No, it's like 73 or something.
You want 25?
Yeah,
77.
77.
So it
20
has
is
been heating up
68.
because you said it started at 70?
30 is 86. Huh?
It started at 70, didn't it?
Yeah,
30.
70 Celsius.
Yeah, that's what he said.
70 Celsius, okay?
Got it.
That's why we're trying to do all the Celsius here. We convert it on them so you know what we're talking about, but then we forget
I
which scale we're using.
see.
But yeah, those first 3 cups should be less.
I have a question.
Yeah.
The same amount of ice, do they have the same temperature?
I did my best, and I measured the ice by how it looked by
Yeah.
volume. I didn't have a scale where I would have measured it by weight, and it would have been a little more accurate as far as having it all be the same mass.
You were saying if there's more ice, it's at the same temperature as if there's less.
No, I agree that if we have more ice, that would be lower.
You think it'd be
But
lower
if
than
we-
this?
Yeah.
If there's
Do they
more
have
ice?
the same?
I don't get it. What if, well, I have a whole bag of ice in the freezer. You're telling me if I bring it in here, it's going to be cooler than one individual chunk?
It will be the same temperature, but it won't last long.
It was cool. No, it was in the same freezer.
But
So when it comes out of the freezer, no matter how much ice you have, it should all be the ambient temperature of the freezer. Right? It should all be about 0 degrees Fahrenheit.
When you first take it out?
Taking more.
heat.
energy.
Well, yeah, it's going to cool the water faster. It's going to make the water cooler. But the ice itself, it doesn't matter the mass because the ice is not going
I
to
guess
cool
it can't
farther.
go lower than negative.
It can't go lower than the temperature outside, yeah. When this hot water cools, it's not going to cool below room temperature, it's going to cool to room temperature, then it's going to stop. It's going to level
That's
off.
pretty interesting.
Yeah, look at this. There's one little chunk left. Which makes sense. It was at 0 C, right? Do you think it's still 0 C?
Close. It's probably pretty close.
0 point close to 1.
Yeah, I would say it's probably still between the 0 and 1. Water, you know, there's not too much convection going on here because it's all pretty equal temperature, but it's very possible that the water that's not right next to the ice is a little bit warmer. I'm getting 5, yeah.
No way.
Now I get 3.8. If I run the ice, 2.8, a little closer. Trying to. This one does feel a little bit warmer than this one, but of course it's my finger. The point is, it's a closed system, but there's still circulation going on, and so it's still absorbing heat from the air, absorbing. It's taking heat from the air, even though it's not all completely melted. In other words, where is the water 0C? Right next to the ice chunk, okay? The farther you get, then it's 0.1, 0.2, 0.3. The farther you are, the farther you are from the source of cold, I guess.
So why is it 5?
Because it's warming up.
Well,
Think about it. There's this little tiny chunk of ice, and the air, it's getting temperature, it's getting heat from the air all over
in
the place.
the long run, I mean, if we came back in 3 hours,
Maybe it would be close to the same.
they would all 6 be close to 25 or 24 degrees C.
Except maybe this one. Now, what's going on with this side here? It's all plugged up.
Condensation!
Condensation? What's condensation? What's going on there?
Yeah, why?
This one's a little bit.
It's one of the 6.
It's what?
It's one of the 6 phase changes.
Thank you,
she
Sue.
said.
Thank you. That's helpful. Which phase change is that?
Now that we've got that cleared
the
up.
gas changing to
A liquid.
Yeah, Nick beat you. Gas to liquid.
Good. Gas is a fluid.
They're both fluids, right?
only
We have to specify here. So why does it happen? Why does it happen? Why does it happen?
because the air, the water was not water cold in the air.
The water what in the air?
Like
So the small water drop in the air.
Oh, a drop. Okay.
So the air has water in it.
I'm going to disagree with the drop part, but
I don't know how to say.
vapor, gas, water, gas, right?
Yeah.
Vapor, not drops.
And needs a cold surface.
And so what does the...
That thing happens.
So this air is warmer than the glass. It's holding some water. You could think of it as having air, or as having water dissolved in it, in a sense. Okay. As it hits the glass, what happens with heat transfer?
What?
There are different temperatures, right? Where is heat transferring? From where to where? Air to glass, right. So, where'd the water come from? All this. Was this originally water that was in the glass?
No.
No, this is all water that was in the air. But with a cooler temperature, the air cannot hold as much water. It's just like you try to pour sugar in cold coffee or salt or something and stir it around, it's not going to dissolve very well. You heat it up, it dissolves a whole lot better, right?
Yeah.
Hot things are more efficient at dissolving things.
Because the particles are moving
Has to.
quicker.
Yeah, there's more particles in contact that can pick it up,
Yeah.
so on. So what's happening here is as the glass saps heat from the air can't hold all the water, so some of it precipitates out. That word precipitation, that's where it comes from, okay? And you did precipitates in chemistry too, right? Where, you got something dissolved and you add some kind of chemical and all of a sudden stuff drops out of it and it's on the ground, even though it was dissolved perfectly clear, invisible before. You ever do an experiment like that?
No, we didn't do any experiments.
That's sad.
Yeah. So.
Well, that's where the precipitation comes from, because water is precipitating out of the air. So, this right here, what did we say this was on the inside here? What's going on here? There's condensation on the inside of the glass.
That's from the steam. That is from the water in the cup.
That is from the water there, because what is the water there doing?
It's evaporating.
Right.
And then now it's condensing.
Yeah, so think of air temperature right above the level, think of the air temperature right above the level of the water there. Warm or cool? Warmer than room temperature?
No.
Probably, yeah. Warmer than room temperature because it's in contact with the water. As soon as that heat keeps rising, now all of a sudden, it's in regular room temperature, and the air absorbed all that heat, all that water that was warmer. Now it gets a little cooler, back to room temperature, and it drops some of it back off. It's got to condense some of it out, because now it's only at room temperature, and it can't hold it all. Does that ever make sense? Okay. Now, steam we were talking about before. What is steam again? It's not here anymore, but what is steam?
Water evaporating.
Is it water? Is it actual water vapor like gas, or is it liquid, or is it solid? What kind of water is it?
Kind of gas, kind of liquid.
Yeah.
So it can only do one, Nick. It
It's
can
a
only do
gas
one.
because I mean, it's gas.
Okay. Let me ask you this: what are clouds made of?
Yes.
Okay. So you're saying the clouds are made of gas. Well, then what the heck is the? Why am I not looking at you through a cloud? If we know there's water in the air,
There's not as much of concentration of gas.
so what? Doesn't matter if I look through a gallon of water at you, I can still kind of see you, right? It's still clear. Clouds aren't, and this is, everyone gets this wrong. Everyone thinks clouds are made of water vapor. That's not true. Clouds are made of liquid or solid water.
It's ridiculous.
Clouds are not made of water vapor because we can see right through water vapor. I'm looking at you through water vapor right now. We know there's humidity in the air. There's water dissolved in the air. I'm looking at you through it.
So it's ice. Kind
Well, no, because it's above freezing. Way up there, the clouds, yes, a lot of them are ice crystals.
of. That's what I mean.
Yeah.
Okay, yeah.
Then what is it made out of in the like fog?
Fog is, you're seeing, it's 100% humidity, and that's why you can still, the air is not only full of moisture, it's got more than it can hold, and so it condenses out into a cloud. That's what fog is, it's a cloud on the ground.
Cool.
Okay? So when you're seeing fog, you're looking through minuscule little water droplets. You're looking through liquid water. So we're walking around in liquid water. Why aren't we swimming? Because there's more air than water. The water molecules are so small they're suspended in the air.
That is so cool.
So when you see steam coming off something boiling, you're not seeing water vapor. You're seeing water that's evaporated and is recondensing right away in the air.
So what
That's your
is
breath
it
in
then?
winter too. Same thing.
So it's a liquid then, or it's
Yeah, it's back to a liquid.
okay.
But then
So it's
the
a
steam
liquid
disappears,
flowing?
so it evaporates, condenses, and then it re-evaporates as it gets farther up because then it can mix with more air. Your breath in the winter, same thing. Your air coming out is so warm, it's got lots of moisture dissolved. It hits that cold air, boom, cold air can't hold the moisture, so it all condenses out into a cloud. But it mixes with all this other air that's drier, and so the cloud goes away and re-evaporates. So there's actually three phase changes every time you're boiling water or every time you're breathing out in winter outside. It's real quick evaporation, then back to condensation, then back to evaporation. How can that happen if water takes so much energy for a phase change?
Because the temperature changes are so.
Big temperature changes are going to they're going to take heat away or add heat very quickly.
Yeah.
Plus, the amount of moisture in the air, there's not that much, right? The water droplets are so tiny. There's not that much water to heat up or cool down.
Don't ever. I was laughing at.
Drink boiling water, done. Okay, I won't.
I was laughing at Yahoo Answers because some of the.
Oh, they're
Oh,
ridiculous.
those are
It's
so
so
funny.
ridiculous that people are.
They should not let anyone answer.
They should not. You should have to leave your credentials.
Mhm.
Because I was looking why water evaporates, and I wanted to see what everyone was saying. 'Cause there is some different theories, because there's a bunch of different factors that come into play. Like, do you guys know what surface tension is?
Yeah.
What's surface tension?
I don't remember what it is. I just remember
We've learned about that.
it.
Yeah.
Keeps that.
There's some theories, and it does come into play a little bit. Like this has surface tension.
You can see right if you look closely right around.
Oh,
you see,
like when
no,
you
see
hit
that?
the water and
You
it's
can
a lot
see
harder.
wrinkles.
Yeah.
Yeah.
If you jumped out of a helicopter into the ocean, you think, oh, that'd be good.
No,
It
you
would
cannot.
actually be better to land on the ground.
No, they proved that wrong in Mythbusters.
It depends. Well, from what height
Look
were
at that, you
they?
see
Yeah.
wrinkles
They
on the
were
surface of the
coming out of
water.
a helicopter.
Like how high?
How high though?
It wasn't like really high.
What experiment are you talking about? I said it would be better to land on soft, muddy ground than it would be in the ocean if you jumped out of a helicopter.
Maybe if you were
Oh,
like
soft
600.
muddy ground. They were doing it.
I think it
Like
depends
a
on
rock?
surface area.
A rock wouldn't matter, you'd be dead either way. But there's been a guy who's jumped out of an airplane before, his parachute didn't open, and because he landed just right, he broke a few bones in his body, but he lived. No parachute, jumped out of a 30,000 foot airplane.
Oh my
His
gosh.
parachute didn't come out, he landed.
You break every bone in your body.
Yeah, he broke quite a few bones. Not his back though, which is interesting. He just happened to land in the correct way. I mean, he landed on his side, and he was fetal. And so when he landed, I think they said he broke his pelvis, dislocated his shoulder, a few other things, but he
That
lived.
must be an awful way down.
All right, real quick before it goes away, look at the look right around the chunks of paper. You'll see
Oh, yeah.
wrinkles in the surface of the water. That's the surface tension.
Yeah.
Pass it back.
But anyways, that has a little bit to do with the whole evaporation thing. One guy just said, water is a mysterious bugger. It does what it pleases. One minute you look away, and the next minute it's gone.
What?
Yeah, exactly. It was like
Okay.
some old grandpa that just discovered Yahoo Answers.
That's.
Okay, now I made it
Back to the use of bugger.
Oh, Mr. G.
Alright, so why then does water evaporate? Because water is nowhere near 100 degrees C, right? This water is nowhere near 100 degrees C. Well, according to our phase change diagram, water needs to be at, what is this?
0. Oh, that's.
This is 0.
Yeah. That's 50.
Okay. This is 100. This is a crappy
yeah.
marker.
No, it's the board that's crappy right now. Nice. Because
That was a good one.
Hold on, before you write, let me just clean it quick. Because you can see all the red smears all over the place.
I don't think that's the marker was. We can't write for a while.
I'll be writing in like 2 minutes.
Um,
It's ammonia based, it evaporates quickly.
but according,
Yeah, Miss Sam always does that. She erases the nights.
really? On mine, it's
There's no class.
it's what?
We have more than 2 minutes. So
Yeah,
don't worry.
it's a long class.
He only says that when I'm talking. He only tries to get me to hurry up.
Yeah.
Correct. You can erase all the cups too.
Oh, thanks.
You bet. Any ideas?
What?
Because we all agree that water evaporates and it's not 100 degrees C.
Yeah?
Yeah.
According to our phase change diagram, that's inaccurate.
Just
Right?
dump the phase change diagram.
What?
Just dump it.
Wait, what's
You
your
can just look at your books. Let's just look in the books with phase change.
So, according to the phase change diagram, this right here is H2O. This right here is ice. This right here is gas.
Yeah?
Well, according to this, we need to be at 100 degrees, and not only do we need to be at 100 degrees, but we need 100 degrees plus a bunch of heat in order to get to gas. Agreed? What? Look,
Only in certain circumstances.
only in certain circumstances.
Well, like, because with the rain and everything, the concrete is hot.
The concrete is 100 degrees, you think?
No, but it's hot.
Are
If
you,
it-
are
And
you-
so
are
when
you
like
saying-
the temperature of the rain compared to the temperature of the ground, it makes, and the sun's heating it too.
Sun's heating it. Do we require light to evaporate?
No, but the heat from the sun.
Isn't that what they told us when we were little? That the sun evaporates water?
The heat from it.
The
Do I
heat-
need to
If
break
there's
up
no
my
sun,
X
we'd
spectrum
freeze.
poster?
What?
If there's no sun, we'd freeze.
Right. But I was always taught when I was little that the only way that things evaporated was because the sun,
Oh, really?
like it was some kind of like pulling it out. Anyways.
It's funny.
What's the sun really doing? It's heating the surface with
Right.
infrared rays. We can't
Okay.
see the heat, we feel the heat.
So no ideas?
Infrared all the way up to red,
Do-
we can't see it.
Why does water evaporate when it's not 100 degrees C?
You were saying the same question as yesterday.
I know, and you never answered. No one answered.
Mr. Ernst doesn't get it yet. That's why I'm asking it again. I'm just kidding.
I don't know.
Is this accurate, or are we saying that this is debunked?
Not in all cases. I mean, it is for normal cases, but I
So
mean,
there's a lot of irregular,
I don't know. I
non-normal
don't
water.
know.
I will tell you that this is absolutely accurate.
So it isn't only measuring 1 cubic centimeter?
Yeah, but you can measure with 1
The-
cubic centimeter.
This comes in. Yesterday they were talking about 10 cubic centimeters. What changes with the volume of water? These measurements do. The change in Q changes for how much heat you require to change phase.
Yeah.
But this part is true for all volumes of water. It's true for all volumes of water. Okay? So then, when water evaporates, are the molecules at 100 degrees C?
True for all volumes at standard pressure.
Yeah, true for all volumes.
So
Yes.
yes then.
At standard temperature and pressure. STP, standard temperature and pressure,
Yeah.
if you remember that from chemistry. So, yes, when water evaporates, then it is at 100 degrees C. How can that be the case? What are we measuring when he's sticking the gun in here?
This.
No, not so. Well, let's assume that we have a real thermometer. And we stick it in there. What are we? We're measuring the temperature. What is temperature, Mick? Change in heat? Hey.
Not
What?
not
Kinetic energy, is there, that's it? Just kinetic energy?
No.
What is it? Average measure of kinetic energy. What's the average weight of us in this room, would you say? Average weight. Well,
180, 200.
I'm 210, AJ.
157.
160, Mr. Gottschalk's 170,
No, I'm 160.
160, 110,
Don't be fat.
120, 130, we'll say. Okay? Now, what's our average quote-unquote temperature? Okay, we're gonna go ahead and do our mass here. If someone said, what's your physics mass? Or not mass. What's your physics weight? Sorry.
Okay, like I
What's your
wanna do
physics
that.
weight?
times 4.
Ooh, 148 and 1/3.
148 and a third. Okay? So our weight in this physics classroom is 148.3 pounds. Agreed?
Yeah.
Now, we go to Six Flags. The 6 of us. And they say you have to be 150 pounds to ride this ride.
And they have,
And the
they
six-
have a big scanner like this that can measure weight.
And the 6 of us go, because we're only 148 pounds, right?
I'm riding it.
I'm riding it. He's riding it. He's riding it. The 3 of us are all evaporating.
What?
You follow my likening or no?
No, that's weird.
Yeah,
What?
Mr. Gottschalk, you do, correct?
I do.
Sue, do you follow my likening or no?
Yeah.
Okay, here's evaporation. You do follow. You do?
Well, which one?
You follow me?
Yeah, but
So
what's
can
the
you-
point?
That's what I'm asking, if you get the point. Alright, evaporation is riding that ride. 150 pounds. 150 pounds means that you can ride the ride. This is a verb, this is a noun, Sue. Verb, noun. 100 degrees C means, yes, you can ride. You can evaporate. That water is going to be able to go up.
But it's heavier.
Okay?
Wait. Oh, never
Now-
mind. Got it.
Alright? So, here is our weight. And so we're all screwed. Right? Wrong. 3 of us are over. You 3 poor saps are under. You have to sit there and watch us have fun riding the ride. In the same hands, in this cup, temperature
So are you saying
Temperature.
some part of the water can get 100 centigrade? Woohoo!
Some part of the water gets to ride the ride.
Remember how we showed you that diagram of...
What's the key word? Hold on one sec. What's the key word with temperature?
Anyway.
Thank you, Sue. Average. This says 20 degrees C. They're not all 20 degrees C. Some of the particles, especially those that are near the top, the surface, do potentially have enough energy and are at individual particles, tiny little individual particles that are 100 degrees C.
Let's say this is...
Capiche?
So you're measuring the area of a bunch of molecules at once. You're getting an average. Now we talked about this, the ones with the most arrows and the most movement, right? Or the longest arrows. Well, those are the ones that have the possibility to jump into another phase, okay? They have the most kinetic energy, and they could evaporate then. Just because of the amount of energy.
It's going to be important
So
that you
this
understand
one
this.
evaporates, and the rest are still there.
Excuse me, Mr. What is that sensation of burning, like you stuck your hand in boiling water? What would that be?
That's just your nerves.
Wait, you stick your hand in boiling water? It's not a sensation. You are burning.
I know, but I mean, like, what? Like,
You're feeling heat enter your body. The heat from the water is entering your body at a very quick rate because the difference in temperature is so great.
No,
And your nerves can sense that.
Are you asking the sensation when if you stick your hand in cold water of the burning? Or, because if you stick your hand in burning water, in boiling water, you are burning.
I think he's just asking
Yeah.
what causes the actual
The
nerves to
feeling.
fire.
no, I'm like, yeah, kind of like the heat rushing into your hand. Is that like, I don't know.
Absolutely, but you are literally burning your skin. If you stick your hand in boiling water, you're burning your skin.
So what
when
is
you
it
take a
then?
shower?
When you take a shower, there's a much
There's
definitely.
also
There is water
What is it
that's
called?
100 degrees Celsius in the shower. Why doesn't that?
Oh, I see that.
This is
Absolutely.
just an individual droplet, a tiny droplet, and that.
Yeah, I
Doesn't
mean,
that cool
stick your
off?
finger in there. Did you get burned?
No.
There are 100-degree molecules in here of water. How do we know? Because in 4 days, this water is all going to be gone. Maybe not 4, maybe 2 weeks. Slow, but it's about volume. It's like saying,
I still think.
And remember, energy is a measure, or temperature is a measure of average kinetic energy.
average.
If you're taking the temperature of one molecule, which is extremely hard, I would venture to say impossible to do based on uncertainty theory. If you take the temperature of one molecule, then you know the exact amount of heat that molecule has, the exact amount of internal energy it has. It's possible it has more than 100 C worth.
Well, it's kind of like this, AJ.
Remember, energy is measured in joules.
Can a fly kill you?
Yes.
Of course. Enough. If there was 100 horse flies and they all bit you at the exact same time,
That would hurt.
it would hurt
so
like
much.
crazy. And would you die? Probably not. If there was 10,000 horse flies and you were standing buck naked like this and they all landed on you and stung you at the exact same time, would you die? There's a chance. Do you follow? A fly.
They bite.
They
Do they fly?
Yeah,
horse.
they bite.
Yeah, flies can bite.
It sucks.
They do. It just feels like and then by the time you go like this, they're gone.
That's possible.
It's the same reason
That's
that
the stupid
you ever do the thing where you gotta.
But hold on, my point was not so that you guys would be standing here buck naked. My point is in a shower. Okay.
Yeah,
Think of,
why?
You ever do the thing where you have a candle and you take your finger and run through the flame real quick?
Yeah. Yeah, I do all the time.
Same thing, right? Why doesn't your finger burn?
Because
It's
it's
not
too
in
fast.
Yeah, it's not in contact long enough for enough heat to transfer. In the case of what Mr. Ernst is talking about, it's not big enough for enough heat to transfer to burn your skin.
And that's kind of the shower. I mean, you know that in the shower there are molecules at 100 degrees C because it's evident. What happens when you take a shower?
There's a bunch of steam.
There's a bunch of steam, so there's a bunch of water that's evaporating.
I understand
And condensing.
what you are
And
saying.
evaporating.
But
you still think it's weird.
Yeah, and
See, I don't know if I agree with the temperature part. I definitely agree with the heat of evaporation or vaporization, but I don't know if I agree that it's actually at 100 C just because
Yeah.
it has that many joules of energy. Because if we say temperature
It
is
can only
average,
just be the particles movement, like
Like
between
when the movement.
air and
Kinetic
water.
energy is the measure of temperature. So each individual, yeah, temperature is a measure of kinetic energy within a particle. And so temperature as a whole is the average kinetic energy of all these. But I have to stick with my guns here, Mr. Gottschalk. For an individual particle to change from a liquid phase into a solid phase, an individual particle of H2O, it must be at 100 degrees C.
I disagree.
At standard temperature and pressure,
You guys hear what he said? He said liquid to solid.
liquid to gas, my apologies, liquid to gas, that individual molecule.
No, I agree with that. I'm saying I don't think there's a way to accurately measure that.
Oh, okay.
Yeah, because
Okay.
100.
And based on that,
Oh, wait, hold on. I want clarification. You don't think that there's
I
a
don't
way?
think we can measure the temperature of just one water atom
Oh, I agree.
or molecule.
So how do we know that this is the case?
Because
Just
you see all the water.
How did they figure
It's a
that?
theory.
It is. Oh, but so is the fact that we breathe oxygen. We don't know. You know.
Yeah, we do.
What?
How is that a theory? We had to, wait, no.
Mr. Gottschalk is
You
saying
would
that.
die. You see it all the time. People like.
Hear me out. Exactly. That's my point.
How's it a theory?
The fact that water's boiling temperature, or that water's evaporation temperature is 100 degrees is as much theory as the fact that we believe that we breathe oxygen.
So it's basically
It's
like.
not a theory.
Nor is this.
Right, but I'm saying
Okay.
we don't know for sure that the temperature of an individual molecule is going to be 100 C. It's
Yeah.
not that much energy.
Mr.
And
you're
here's
saying
why.
Hold on, let's see who talk.
temperature is the average kinetic energy.
Thank you.
Yeah. So you're using temperature to measure the not the average.
Right.
So how?
We're using temperature to.
Always say
We're-
that all molecules
simple-
always
Use
evaporate.
to
All right, here you go, Sue. Do you have an average weight? Right now, can I say Sue's average weight is blank, 120 pounds or whatever?
No.
Can you take the average of one thing?
No.
Mathematically, absolutely, you can.
That's why you can't say my average is how many kilograms or
Yes, you can.
my average.
Sure. What's the the definition of mean? The definition of average is total number divided
And
by,
that's why I'm saying,
or sum of
Oh,
total.
you mean amount of.
since
crystals.
temperature
I
is
got
an
it.
average measurement by definition,
Yeah.
if you have just one, it's not an average, it's specific.
Yeah.
There's no way to measure that because we don't have the technology to zoom in on one thing.
But I mean, you have like the 120 and then.
We
divide by one.
base it off of
This
um,
is Heisenberg, this is uncertainty.
just hold on. We base it off of pattern. So the fact that when we have a large mass of water, we can break down. What's the temperature of the ocean? It's about 50. Now take one scoop out of Antarctica and it's going to be less. Take one scoop out of near the equator and it's going to be higher. But still, the average temperature of the ocean is 58 degrees as a whole. But then, when you break it down, we can look. I mean, there's no other explanation, because if that was the case, if water evaporated, Mr. Gottschalk, when it wasn't 100 degrees, then why is this not all coming up right now? When it's 70, why doesn't it all evaporate?
Because regardless of temperature, it doesn't all have enough kinetic energy.
Temperature is kinetic energy.
And that's where I disagree with you.
I struggle with that because that's what the way.
If I run super fast, I have a whole bunch of kinetic energy. Can you say that I'm really hot?
Well, everything's relative. If you run super fast, absolutely you're going to be super hot. I'm talking about the speed of light. You're talking about 20 meters per second,
What if I ride in a car at 100 meters per second?
100 meters per second, you're going to heat up. If you ride at the speed of light, you're
Am
gonna
I
be on
gonna
fire.
boil? Am I gonna evaporate? No.
At speed of
I
light,
have
you
no
go.
energy. No, I'm not.
There's a lot of
If you could take a car and travel at the speed of light, you're gonna tell me that you're not going
We're
to.
off of the question.
Yes, because then time would not be moving forward anymore.
That's theory right there.
Yeah.
Go ahead.
If we have particles that is 100 Celsius,
Celsius.
why it doesn't change like transfer energy within the water?
Hold on. Repeat here. Repeat.
You were saying the water on in the cup, the side of the cup
Yes.
come from the 100 Celsius particles in the water?
Yeah, the evaporated water.
Yeah, so why it chose to evaporate?
It doesn't
Instead of
choose. That's my point.
It should exchange the energy within the water.
Correct. But it's not all. All of this water. How many particles are in here? How many molecules? Billions. You know? They don't all share the exact same amount of kinetic energy. Some are moving faster than others. Others are moving slower. The reason that we evaporate is because some of those particles do in fact reach the 100-degree plateau.
So,
Those are able to then escape and become gas.
so when you're boiling water, like the water in the pot is not 100 degrees.
The water in the pot is 100 degrees
Why is it still liquid?
because they don't all escape at the same time.
That would be odd.
It would be as soon as, yeah, it would just go. It's not, I'm not telling you that every single molecule at 100 degrees C. I'm not telling. Don't get me wrong here. Look at this line. This is all water that's 100 degrees C. And I'm not. Don't get me backwards and forwards. This is not a biconditional. This is a conditional. If a water molecule is at 100 degrees C, it has the potential to become steam with the right amount of heat. Not every water molecule at 100 degrees will evaporate. However, in order for a water molecule to go from a liquid to a gas, I'm saying that individual molecule must be at the 100-degree threshold. And I don't know that you can disagree if you're being honest. I don't know if you're trying to play.
No, I'm not.
Okay.
I'm not. I'm being completely honest here. I think that
I agree. Everything you said, but just the 100. So,
But
I'm saying
Does
that
everything, are you saying that everything will evaporate?
we'll leave this. We'll leave this here.
but
Where do you want to leave? You want to leave it in the
Here's
window or you
one.
want?
If you heat the water,
Put it
if you heat
inside
the
the
water
can, that way
into
we won't,
100
What, Sue?
100 Celsius, if you heat the water into 100 Celsius,
If you
will
heat
that
it,
turn into the thing,
if you heat it to what?
the water?
To 200,
100.
100 degrees
The
Celsius.
whole thing is 100.
So
Okay.
why
Are they
the
all
whole thing?
gonna
But
become
why?
Hold, let her finish.
So you don't interrupt me. Why can't I interrupt her?
Are they all become the?
Will they all become steam? Yes, but not instantaneously.
It's
Why
not.
not?
Boom.
Why not? Because of what I'm saying. That it's not a biconditional. Okay? If H2O is 100 degrees C, it can become
Vapor.
gas, vapor. Okay?
It can, so it doesn't have to.
It can. This is the word. Can, what's the difference, Sue, between
So-
can and must? You know?
Yeah, but
Okay.
why not?
Why not?
Why not all of them become?
It's an average.
Latent heat is why.
Let me.
This, do you see?
All right. When you're boiling a pot of water, it's not all at 100 C. That's the average temperature. Some of the molecules are greater than 100. Those are the ones that are evaporating. Some are less than 100. Those are the ones that are staying liquid. It's an average. Okay? They're not all at 100 C. Some are more, some are less. Some are right at. Yes?
Okay, so if the cup is evaporating, how the heck is like the last molecule going to become 100 C without us heating it up? Like how does it evaporate without?
That's a good question. It saps heat from the air. So you and I think, are in agreement
So it'll be
that it's
colder
very
in there?
hold on. That it's very easy for this cup to receive or to become 30 degrees C, right? Because let's say we're 25 at room temperature, it gets some heat from light. Okay, so it's easy to get 30. How does it go from 30 to 100? That's a good question.
That's kind of where
Where you're coming from.
But the thing is, air has an inherent want to hold water. It has a capacity to hold water, and if it's not 100% humidity, it's going to be trying to absorb water. And so all those air molecules passing over that one water molecule are going to transfer a little bit of heat here, a little bit of heat there, a little bit here, a little there, until it reaches, it gains
So
all
like
the
it
heat it
condenses
needs
the heat or whatever to each
to
little
jump
part.
into the atmosphere. Yeah, and
It's
absorb
just such a
vapor.
big difference.
It is.
Yeah, I
30
know,
and
yeah.
100?
And
I
that's why
didn't
I'm
think
saying.
about it like that.
That's why I'm saying I don't know that we can measure that to be 100 degrees, but it still needs the same amount of energy to get there.
Yeah, that's why I was freaking out. Like, this doesn't make sense.
I'm not saying, okay, I think you're misunderstanding. I'm not arguing with you as much as you think.
No,
Okay?
I'm no
saying-
longer. I'm no longer. I understand. I'm now struggling with what I said because of what she said. Because I can buy it if we're given a large quantity of water like this. I can buy that there are 1,000 molecules right now that are 100 degrees C.
Yeah.
You know, because there are a billion in here, and I understand the concept of average. You know, that there's probably a couple in here, there might even be a couple in here that are 0 degrees C. A couple of stagnant, non-moving molecules of water. I think you have to be in agreement with that, but there's a couple that are moving around real fast. Those are the ones that are evaporating. It's a slow process, but I struggle with the fact that yes, once you get down and you're talking about 1 or 2 molecules, but see the thing is with that, you wouldn't be able to see the 1 or 2 molecules.
Yes, but if they have to evaporate, I mean, they're not.
And that's where maybe it is 100 C because we don't have a way to measure it, you know?
Right.
We don't have a way to measure something
Well-
that's small, we don't have a way to feel the heat because there's not enough heat coming off of it for our hand to sense or anything either. Usually there's only 1 or 2.
Sue?
Do we see the thing in the cold water?
Specify thing. What's the, do we see the thing you said? What's thing?
Vapor.
Oh, vapor.
Vapor. Do we see the vapor in the cold water with
Do we,
ice?
we can't see vapor.
Vapor is
No,
water
I mean,
gas.
is there any water within the cup?
One, yeah, like
Around here,
Oh.
in the cup with the ice and cold water.
Here,
Yeah.
do we see? I
Is
don't.
there any? No.
Is there? I don't know what
Is
you're
there any
asking.
what? Water vapor above the surface of the water?
Around here, there's no like as the other.
Oh,
cup
right,
or
right.
the cup.
I don't understand what you're.
there's
She's
no
saying there's no
condensing.
condensation inside this glass.
Oh, like there was inside of this.
Yeah.
Yeah.
Yeah, there's also there should be like you said the 100 Celsius particle in the cold water, but there's not.
I think just because
So
there's
There
not
are,
enough.
would you agree though that there are still some water molecules evaporating from every glass here regardless of the temperature? Even a glass of ice water, there's water evaporating from there. It's going to be a whole lot harder for it to do. It's going to go a lot slower, but there is water evaporating.
I'm trying to make like it should be like
I'm trying to make.
Because just like the average, the average of this is 0 degrees, but some of them are moving fast enough to still get into the air.
that's particles movement, not because of the temperature.
That's kind of what I was trying to
Yeah.
get at.
Because they move so like
But
fast.
hold on.
And then the air is able to
dang it.
carry it.
We're
We're going around in circles.
no, we're not, because we keep saying that has to do with the particle's movement, not temperature. And it's like saying that has to do with my definition. That has to do with my my snot, not my mucus.
But the thing is,
Well-
particle movement is at a certain temperature.
Particle movement is temperature. You know?
Yeah.
The water,
I just blew my snot. No, I just blew my mucus.
the
idiot.
water,
Mucus
the
is
particle
snot.
in the water, they can move without being 100 Celsius.
And I would disagree with that because in my understanding of temperature, it is particles' kinetic energy.
And how does it move? Like, how does the I'm still going back to the last two molecules.
Yes.
Or whatever. How does it move?
See, and the one thing I'll say about the last two molecules is that I don't know that it's ever at a two molecule type thing.
Then not all of it can evaporate. Which is what I was saying before.
Yeah, and I don't know to that. I don't know that. But what Sue is saying is that, I think anyways, she's saying that the particles are moving quickly. That has nothing to do with temperature. Is that what you're saying?
It can't go down that low because the molecules are still in the air, right?
The molecules are still in the air?
Yeah, the water molecules. It's stuck in there. The water has to go somewhere.
Right.
And so it's in the air, which is in the cup also. So it's never
There's
gonna
no
let it
air
go.
in the... Well, there is
I
air.
mean, like, the air is going around
Think
in the
about
cup.
heat and not temperature. How much temperature? What's the temperature of the air inside my hand? Roughly room temperature, right?
Yeah.
What's the temperature of the air in this whole room?
Room temperature.
Which one is more heat?
Your hand.
The one in your hand, I agree.
Yeah, because the heat of your hand is.
All right, so you're rephrase. Which one has more kinetic energy?
Depends which
I'm talking
Yeah.
quantitative. I'm not talking average.
Which molecule are you talking about?
How many? Okay, are there more molecules in my hand or in the room?
The room.
Okay, and if the average temperature of those is, whatever, 20 degrees C,
I don't like
and they all have a certain amount, they have an average of a certain amount of energy, right?
Yeah, but I mean, the
Here
heat
I
of
have
your
a billion
hands-
particles. In the room I have 10 million trillion particles. Which one has more energy total?
Come
Come
the
on.
room.
Yeah, right? The room. So there's more energy to be transferred to the water. All that heat is transferred because more air can be in contact with the water. So it's like a, I don't know, it's like a conveyor belt.
So
You
does
get
that
a little from you, a
does
little
that
from you.
mean that does that so here's the thing. This is my guess. Is that God created water to have an inherent want to evaporate. Because if water did not have an inherent want to evaporate, the water cycle could not exist.
But the only reason it
Which-
wants to evaporate is because air has an inherent want to absorb it. Or
Right.
make it evaporate.
Right. But that's what I'm saying. Is
Only
that,
to a limit. To a limit.
okay, is that water has an inherent want to evaporate, aka air has an inherent want to suck it up. Science never sucks to absorb that. Because if that wasn't the case, then we could not have the water cycle, wouldn't have precipitation, wouldn't have plants that grow, wouldn't have rivers that flow. The water cycle would not continue itself.
We're not saying the water can't evaporate.
But, okay, so hear me out. So because water has an inherent want to evaporate, and air has an inherent want to sap water into it, that, as Mr. Gottschalk said, what has more energy? The air in this room or the air in his hand? Yeah. The air in the room collectively has a ton more energy. It's possible that that air can concentrate energy to this to the point where it's going to have enough kinetic energy to get those particles to be at a high enough kinetic energy so that they would then join that air.
If I put this right next to where is it? Here? All right, let's cover one up. Which one's going to evaporate faster?
The one that's not.
Right, because it has contact with all the rest of the air. The other one does not have contact. The air inside is going to reach a maximum humidity even if it absorbs heat from the ambient temperature around the glass.
I have another glass.
Can you have another glass?
Yes.
Yes, yes.
The air can resolve some water.
The air can resolve some water?
Is that the word resolve?
Resolve. Are you talking about one of the 6
No.
phase changes? I don't know. Resolve, what context?
Resolve.
Dissolve.
Okay.
The air can dissolve some water? What does dissolve mean?
I don't know. I'm asking you a word.
I'm not sure which word you're looking for. Dissolve
You put the salt into water and it's
dissolves.
okay.
Yeah.
Dissolve.
Dissolve. So you're
And
saying that
when it gets hot, like the air gets hot, it can dissolve more water.
I agree.
And then when it gets to the
It's always more humid.
top.
Sometimes.
Yeah, most of the, that's why typically we associate heat and humidity because when we have, that's why the Midwest is both hot and humid is because there's more water here than there is in Arizona.
More available for the
More
air.
available for
Yeah,
the
Arizona
heat to
wants
take it
more
up.
That is why
But
we're
I think we're going back to proving this, proving the fact that it's 100 degrees, it requires 100 degrees. Because when we put this thing in here, he's got it covered up, we put that in there. We have one identical cabinet with the exact same setup, and it's 5 degrees warmer in Mrs. M's room, which is going to evaporate faster.
Yeah.
The one in Mrs. M's is 5 degrees
It's hotter
warmer.
and not more heat.
Yeah.
Because it's got more heat. Right? It's got a higher temperature, hence more heat, hence more kinetic energy.
So what's the point you're trying to make?
The point that
This
I'm
class?
the point that I'm trying to make is that
We need 100 Celsius particle to evaporate.
yes,
Okay, but I never heard any particle that has a temperature.
you never what?
Heard particle have a temperature like
You've never heard of a particle having an individual temperature.
yeah.
If you understand the
You make
context,
this particle
if you-
totally different.
if you understand the context of the word average here, you would have to agree that each particle has an individual temperature. That each particle has its own individual kinetic energy.
What's the average of this? If I just write the number 3, what's the average of 3? Is it 3 or do we say we can't find an average?
We say it's 3.
This is 3 divided by 1.
3
Yeah.
divided by 1, yeah. Now, here's the thing is, the word average actually means normal. So, in the English language, we use the word average. What do you think of? Which measure of central tendency when I say average? Measures of central tendency are mean, median, mode. Which measure of central tendency do you think of? Mean, median, or mode? Mean is generally what you're taught. Average can actually mean any one of those 3. The average annual income in the United States is $45,000. Okay, the average family income in the United States.
Yeah.
Guess what the mean income is in the United States?
You have no idea.
I don't know exactly. Sorry, so nor is the average exactly 45. These are rough estimates, but I do have an idea, Sue, thank you.
What?
But the average that we would say is 45,000, the mean is around 200. Why? Because of things
Because they're
called
super rich people.
outliers, right? But we don't say that the average income in the United States is $200,000 per family, even though that's the mean. And the reason we don't say that is because it does not typify. It does not paint a good picture,
Yeah.
because that's not the case. That's not the normal family. In that case, average is better shown by the median is what we use there. The median income is 45,000. Median is the middle number. If we take high, low, we're finding the middle. That shows a much better picture of the normal family in the United
Why can't
States.
they just do the mode? I don't know why they never do that.
The mode, well, because if you think about mode is really tough because mode, you're going to go all the way down to the cent. And so it's possible that more people make $65,321.07 per year than make, you know,
I see.
where mode can be a little bit ironic or fluky, if you will. So average is going to be the most typical. And in this case, Mr. Gottschalk, you would say that average means mean for this, right?
Right.
Average does in fact mean mean in this. But
I'll concede, I mean, that the water may be 100 degrees C or greater to evaporate
I don't think
if we could measure it.
yes.
We can't. And
Right.
because
I agree with
it's
that.
completely random. We can't say, okay, this molecule is the one with the most energy, that's the one that's going to jump. We can't do that because it's based on random collision. It's, you know, that's the
Yes.
important part.
And I agree with you there too.
So we can't.
So is it theorized? Yes, I agree with you.
It's
But-
kind of like an obvious theorized though.
Yeah, I agree that because of all of the patterns that we've seen, I don't think that it is as much theory as what we're saying. You know, the fact that this table is there, the fact that this is in print and you've seen it in chemistry and now you've seen it in physics, and you probably have seen it before, Sue.
What?
This
Yeah.
and Mick, China, Thailand, and America all teach the same thing. To me, that means it's less theory than what we're presenting.
Yeah.
I mean, the bottom line is there's a ton of stuff that we talk about that is frankly inaccurate. Did this travel in a perfectly I was thinking you were going to catch it. Does that travel in a perfectly parabolic motion? Absolutely not. Should it? Well, yeah. If there were no air resistance, you know, and there's a lot of stuff that we talk about that's based upon theory, and this is probably one of them, sure. But
I guess what I'm getting at is if it's one molecule, we don't need an average. Let's just say how much energy it has.
we can't. You just said that. You know, it's impossible for us to say to find
And
the.
that's what I'm saying, yeah. How do we know that if I have 1 milligram of water, that if it's 100 C, it should have 226 joules of heat? Can I say that? You know what I mean? Why not just say if I have one molecule, I'm just saying if I have one molecule, I don't need an average. So I could just say heat. The average person in the world doesn't understand joules as well as they do temperature because we're all so used to average.
I agree.
But if it's just one thing, there's no need for an average.
I agree.
What the heck?
So where are we not agreeing?
You're saying we shouldn't include temperature whatsoever in the in evaporation, or is that what you're saying?
For one molecule? No, I don't think we should. Well, think about it this way.
Do you guys understand what he's saying?
Not really.
No. He's saying that I keep going back to this point because Sue kept asking, you know, what's the point of trying to make? And I kept going back to the fact that a molecule must be 100 degrees Celsius in order to change from a liquid to a gas. What Mr. Gottschalk is saying is, let's not even equate temperature with evaporation, because temperature in itself is an average,
And it's based on standard temperature and pressure.
and it's based on standard temperature
Or
and pressure.
standard, the pressure is the more important part.
But here's the thing: is average insinuates that you're talking about multiple molecules, right? Does water evaporate with multiple molecules at the same time?
Then what was the point of the average energy of kinetic? Because if you're saying the temperature is average, then what the heck is the point of saying it's the average?
So, and I think I agree that
Because
I
if
don't
it
know.
was amount of heat, if heat equated directly to temperature, wouldn't the graph look like this?
Yes. Yes. Yeah, it would. We showed that to be false yesterday. That our temperature and heat directly proportional.
Or kinetic energy, I should say.
Our temperature and heat directly proportional? No, absolutely not. They're not. The thing that now that you're saying that, I agree with is that who invented Celsius? Mr. Celsius. Yeah, what was his name?
I don't know, Ferdinand maybe?
Ferdinand Celsius. You know, where that's kind of a man-made idea.
I don't think it's Ferdinand.
And it's a relative term. What is it relative to? What? Fresh water. It's relative to fresh water.
Anders Celsius.
Under Celsius.
Yeah.
It has to do though, because I keep going back. It's relative to fresh water, and so, you know, the thing is it's none of this.
Relative to fresh water at standard pressure.
Yeah.
Also, you know,
That's true.
there's so many variables,
Yeah, you're
and
right.
that's why I don't like equating it to temperature.
Well, and the other thing is we're looking for a concrete blanketed statement. A molecule at this temperature will be. You know, we were measuring these, and it's still all an average. And I mean, there's probably particles in here that range between, I don't know, -5 degrees C and
But then
20 degrees C.
you also get other different things in there. It's not pure water.
Water.
And so when you go down to one molecule, it is pure water, which would make it different.
Right.
With this,
Hey, once again, all right.
No homework.
I know, right? You'll be like,
We're going to not talk about this more, but Mr. Gottschalk and I are going to come to a consensus here after reading through some things, and we will give you a short 5 minutes conclusion on Friday.
When?
Friday.
No, I mean when?
You said when, I said Friday, you said no, I mean when.
I mean, when are you gonna talk about
We
this?
want to give them homework.
Friday.
Within your YouTube.
Oh, within us two? Between now and Friday.
Yeah. Now, we didn't talk about anything that we need to for homework, so we're just not doing homework yet? Okay. Maybe if I don't know, I'll find time this.
What's up there?
what about noon?
No, it's still got you.
There's no way you can. I can talk to, I know the Rocket Lutheran AP guy, and so if you wanted some proof that you can't do it in 1 year, I think you can provide that. And also, I think I could probably get a curriculum for you. I don't, because he teaches the AP, he doesn't do any